because half of you guys are here today. You are, oh yeah, so sometimes you're across the world, and now you're here. Good.
Well, I figured I'd get you for when the labs start being non-virtual. That way I don't disrupt the class when I slip out.
That's, this is nice.
I managed to find the streaming text on Amazon. So
Amazon, okay.
I got used one for about 9 years.
I don't know what the rules are at this point. Like, just since these are not available, it might be okay maybe to share the virtual copy. Also, let me look into it. Okay. So
I
then
know that Dr. Talabatra said, "Oh, you should be able to find the PDF online." And I found it in a few places, but it was one of those that I don't know if I trust downloading anything.
Yeah. There is one website which I think it is okay to pass along officially. That's called archive.org. Probably you guys are familiar. They don't put, or they at least try to weed off all the pirated versions. But I don't expect this to be there. Archive.org, not ARXIV. That's for papers. This is, but I must have looked there already, and I would have, usually if I find that, then I place a link to that. But this is not expected to be there because this is still in. Usually, I think there is some US law saying that after 70 years or something, there's some number 60 or 70, then they are allowed to put it. And not on internet, at least the copyright does it. All the old books are this.
That's true for everything except Disney stuff.
Oh, really?
They found a way to bypass the law so that none of their stuff goes public.
I see. So maybe we can do the following. I am allowed to post chapter-wise, and especially if it is behind the password, like on D2L, then I can put in like 10 chapters, or if there are 20 chapters in a book, all the 20 chapters, as far as it is chapter-wise. As an instructor, I can do that. So what I can do is, I can put the first couple of chapters of the book under D2L, right? It's just a matter of scanning. So if you don't mind, we just send a one-line email about it so that it stays in my memory.
Okay.
That you suggested that you will try to do this. I think that's won't violate any policies. Yeah, hopefully. So you guys mind me putting you guys on this for a moment so that you guys they see you. Assuming I have to the right side so it doesn't go off. Ah, here you go. Okay.
Hey, the petting zoo.
What is it? Petting zoo. Oh, I see. When you see this. That's a good one. Okay.
I've been on so many Zoom meetings in the past 6 months that I hope they don't decide it causes a disease.
When did I press? Sorry, one moment. I can set it up. Oh, Avinash, are you on in campus? Oh, we cannot hear you.
Huh?
Avinash, we cannot hear you. I just wanted to say that there is room here in the classroom. So if you're interested, you can join. It's up to you. I don't think he's hearing either. Oh, yeah, so he did. Okay, hopefully you did this. Come on. Okay. So we have homework 1, order 2. Let's transfer this Monday. And earlier I have said this is also hard copy is okay. I'll still accept it, but it is, I think, more organized if you post it on video. So, and again, if you have any issues with that, just keep doing it. That's also perfectly fine. I like to grade it physical copies, but when it is half online and half this thing, I think I'll prefer everything in uniform. That's all, not really difference. Oh, there's one more midterm. September 13th. Monday. This will be in class. And for Khalid, we have to talk about it. You cannot be in class. And extra credit problems, yeah, I did notice that most of you guys posted it. Usually I'm very quick at it. I just see participation and give it. So that's what I thought. I think that's why I got late for this. I was thinking 15 minutes back, I started reading the questions that I gave. And most of you guys really wrote nice things about finding the error and the grades. So that was so thanks for writing. So I started reading and I paid full attention to it. But you'll get your grades for that. But thanks for writing your thoughts on it. It's I never thought I'd get such a feedback by making an extra credit question. It was really useful. So, but having said that, I don't know how to incorporate it myself. And many of you pointed that yourself that you guys also don't know how exactly. So I don't have any clear solutions to that. But I do acknowledge that there is a huge amount of error in the grading, the way we grade, which is never addressed. Right? So at least now that I know you guys know exactly what I was talking about, so at least we should all acknowledge as a whole thing that there is a lot of error, especially in a physics course where errors is everything. Science, so we should acknowledge that. Okay. Okay. So that's about the logistics. Yeah. So let's. We are sort of jumping around in between the courses. So I introduced the concepts in the other course, but mostly index notation. I think Avinash, you are not there in the other course, but you have covered it in some form. You sat in my course before. So, so we were talking about a gradient operator. Which is just, this is sufficient. Okay, so the gradient operator as it sits has a meaning. So it's exactly like when you say a vector is A. I don't really have to give you its x component, y component, z component to say for it to be a vector, but often that's also a representation. So, so from this point on, the equal sign, that's just a representation and a convenient one. E by dx plus I sorry k by I plus k by dz. So that's in rectangular coordinates. What is its representation? And let's say let's begin with cylindrical coordinates. So this is rectangular coordinates. And typically, I think it is most of when we do vector calculus, it is we stick to rectangular coordinates just because it is easier. But you might have seen it here and there if you've taken some courses on quantum mechanics, differential equations. You tend to use this. So, what is this in cylindrical coordinates? Let's say cylindrical coordinates. Cylindrical coordinates. It is let's say rho phi z. Is that familiar? Rho is in a plane. You have a radial vector in a plane, angle phi and z. In terms of that, any guesses of what this would be? Even guesses are okay. What do you think it might be? Yeah, rho hat, right? Right. Rho hat. So there will be surely three of them, right? Three. So this is phi hat and z hat. Always three unit vectors constant, and then it's a matter of what those operators are within each direction. Yes, Avinash? Yes. So this is d by del rho, yeah. And this is 1 over rho. Good. Very good. What is it? Very good. Right. So, and then the question comes, oh, how do you get this, right? So it's at least one way to see it. But before we go there, let's do spherical also. These are the standard ones that we'll use. So this is R. By the way, my R sometimes looks like gamma, so be aware of that. But once you realize that, then it's not very hard. Except we reach a stage where both gamma and R is coming together, which I try to avoid as much as possible. Yeah, so that's how. So R, theta, and okay. So this is R hat, this is theta hat, and this is phi. Right? Anyone remembers this again? Any chance? Yeah. Yes. Not Oscar. Just R. Yeah. R. Delta theta. Very good. One. I'll go this side. Phi. Yeah, it is R square when you do the del square, and that's one of the good. So how can we get this questions? No. So notice at this this quantity here, rho d phi and dz, that has a special meaning. Best is to look at a circle. So this is let's have two circles actually. But volume element and cylindrical coordinates would be like this. That's your area element, and let's say this is your x and that's your y, and z is coming out, right? So z element remains the same, dz, but this is no more a rectangle. But in the small, infinitely small case, of course, you can approximate it as a rectangle and you don't lose anything. But it is not, when you take an area element, it's not. And here you realize that you can take the inside or outside to the leading order, it is the same. And this is your row d5. So this is d5, and this is row d5. And this line here is your d row. Is that visible across? Right, a little small, I know.
Yeah.
Okay. So you see that first get the radial direction. What's the line element in the radial direction? So notice radial direction comes, we should remind ourselves, how do you get the radial direction? Our hat is, yesterday we pointed out that it's the gradient of the circles, right? Gradient of this surfaces in 3 dimensions, it is of constant radius. Surface of constant radius. Oh, I was doing rho hat, right? So in rho hat, right? So surface of constant rho, and then divided by the same thing, magnitude, so that you make a unit vector out of that. Is that clear what I mean by that? Right. Let me expand on that. Surface of constant rho. Let's work, since often we are friendly with rectangular coordinates. This is gradient of surface of constant rho is square root of x squared plus y squared is a constant. So this is a constant. So that's what it is. And this is gradient of the same.
Bad.
So this is the constant doesn't matter. Derivative of that is 0. So that's I hat d by dx of square root of x squared plus y squared plus j hat d by dy of square root of x squared plus y squared plus k hat. It is 0 because there is no derivative with respect to the x squared, x and y are dependent. So, and then I have to divide it out by the magnitude. So, if that makes sense, right? The magnitude of that vector. What is this equal to? So this is I hat times this goes in the denominator, and then there is a 2x, right? So it is x over square root of x squared plus y squared plus j hat y over square plus y squared plus 0. And in fact, this is actually, if you notice, this is already a unit vector. So I don't have to actually divide by that quantity. And this is your rho hat. Okay. Yeah, that's a definition of rho hat. I guess I cannot write anything else, I suppose. But yeah, I cannot. Yeah, I deal with that. Right? So what I was saying is, yeah, why I went there is that this is rho hat direction, and the line element. When you think of it as an area, the line element along that direction is d rho, and that's what shows up here. Similarly, your phi hat at a certain point, let's say here is in this direction, so that's your phi hat. And these things depend on coordinates now. We'll do this explicitly much more or a little bit more in detail in the next week, where we will actually see the properties of this coming from a little bit more from the scratch, and you will see that already you can see that this is actually dependent on the coordinates, and the phi hat direction is rho times p5, which geometrically it is very visible, and in the z direction, this is in the z direction, this is dz, so that's how you would put. Same thing if you do that for spherical polar coordinates, you get dr, so the line elements here and spherical polar coordinates will be dr, r d theta, and r sine theta d phi. Okay. So that's your line element. Can you motivate this? So that's an extra credit problem. Let's say motivate this. If you can derive, that's great. But motivate this in spherical polar coordinates. Notice I didn't really derive this at this stage, right? We can, but that will wait for until we got to. Okay. So motivate this. Why it is this and spherical, at least diagrammatically. Let's say. Yeah, do this diagrammatically. Yeah, so extra credit problem is to derive this diagrammatically. So draw a diagram and show that. It's going to be hard because it's a 3D diagram, but it helps. It will be useful. Okay, so that's how the gradient operator comes by, and there was one more thing suddenly struck me that I was wanting to know. So that's all. Yes, the point is that there's also the point that so here I said this is an area element, that's a vector, right? So it is a cross product of this direction and the set. So area is always the cross product of the two sides. So that's something that you want to keep in mind. What about the position vector? So this is the gradient operator. Right. So this is the gradient operator. So there's also a position vector, which is usually much more easier to see through. Correct. So I ask again. This is R. That's R. And this is in rectangular coordinates. I'm sure this is familiar. Y, J plus Z, K. Right? So that's rectangle. What about in cylindrical coordinates? What is the position vector? Or let's work with spherical coordinates. So first, let's do it in spherical coordinates. What's the position vector in spherical coordinates?
It's just R hat.
Right. Very good. Very good. Very good. Yeah, that's great. That there'll be a tendency to write all the components. So it's just R hat. Very good. Right? So this is plus 0 theta hat. And what is cylindrical coordinates?
Can you zoom the front one a little bit?
Oh. It's
Close. Yeah, okay.
one more, I guess, right? Yeah. That's there's a length of R in the R hat direction, and there is no component. Position vector has no component. Then what about in cylindrical coordinates?
Rho hat.
Yeah, rho hat. Yeah, good. That's it. This cannot be completely correct because its length will be x squared plus y squared. So it's all. It turns out that so this is 0, there's no, in the phi hat there is no plus z and the z hat direction, let's say. So, which is the same as k hat direction. So it's only this piece here compressed and that's so that's a good thing to realize. And I should also say it's good to probably you're aware to a certain extent. There is very few coordinate systems in which we can really work things out most of the times. And those are these three coordinates: sphere, cylinder, and rectangle. If you say take a differential equation, in fact, there was a I don't know how much it is true that it's a conclusive or not conclusive, comprehensive one. But at least the statement was back in 1930s, which is a pretty standard even today. We all believe in it, and that's that the differential equation L squared. This is the most common differential equation that comes in. It's called the Laplacian. We will see this can be solved in 11 coordinate systems. So there are three: rectangular, cylindrical, spherical. There are parabolic, there is elliptical, spheroidal. So there are some 11 coordinate systems, and you can solve this differential equation. And at least the statement seems to be that that's it. There is nothing else. That I'm not very sure how comprehensive that is. Maybe we didn't explore sufficiently. Usually it is harder to say that it is not possible to do it in anything else. But even to the fact that we know only 11 of them is a big deal. Big deal. I mean, you realize that it's a small set. And we are doing electrodynamics. When it comes to electrodynamics, there is a slight difference. It becomes a vector differential equation. So there's some vector nature because we are doing electric field. It's not a scalar quantity. We are interested in vector field. That reduces this significantly. No more 11. And if you really stick to complete electrodynamics, just 2. Okay, even cylindrical is not easy. Just rectangular and spherical is the only 2 exact solutions possible. Cylinder is too hard. Right? Unless you take extreme limits where you take a perfect conductor and all that, then it's very much possible. But rectangular and spherical is what you can think of is you might have heard of in electrodynamics that things split into 2 modes. Is that a familiar? When you think of light, right? You might have heard of 2 polarizations, right? Think of a motion of light going in a certain direction. There is in the plane perpendicular to that, there are 2 directions. It is not the direction of electric and magnetic field. Doesn't have to be. Like you can always choose it to be in the direction of electric, and it doesn't have to be at all. There are 2 directions, and in those 2 directions, this whole electrodynamic, the Maxwell's equation split into 2. Like there are 2 independent modes that travel through. That split, it seems like it should always be possible, but that's possible only in rectangular and spherical coordinates, not always. And there's very special scenarios when that happens. And in that case, there's a lot of simplicity, and you can proceed and do a lot of analytic calculation. But otherwise, you're just in the dark, or often then you have to depend on models. So it's very hard to proceed. So that should give you an idea of how much symmetry matters. So again, there's a position vector and there is a gradient operator. Let's deal with those 2 things and let's and let's see the following. Okay. So now there are 3 operations you can think of. Operations, vector operations, let's say. And I will differentiate between these 3. One is the grade. There are 2 vectors now. That's gradient operator operating on the position vector. But then I will also talk about the gradient operator acting on the position vector, and there being a dot product. And I will also talk about the gradient operator acting on the position vector with a cross product. Okay. Now, if I take a dot product, so let's start with the second one. Is this a scalar or a vector or a tensor?
Scalar.
Right, so this is a scalar. Gradient operating on a vector, and notice this is a gradient operator, so we have to be careful there a little. I'll come to that very soon. What about this? Right, so this is a vector cross product of two vectors. But again, with the caveat that this is an operator. So this is a vector. And then comes this. Right? What is that? That's two vectors. Now I haven't said this is a dot product or a cross product. So this will be a tensor of rank 2, or we will call it a diagonal. The best way to see this is sometimes if you have a vector A. So if you have a vector A and a vector B, this is an outer product. Like often we write this as an outer product, especially in quantum mechanics. We use that idea very much. Like A was equal to AX and Y, let's say, and B was equal to Bx times By. So then A outer product B is as a matrix, if you think of it, it is AY. So this is a column vector multiplied by a row vector. Okay. And that's equal to AX, BX, AX, BY, AY, BX, and AY, BY. In this way, it is, notice the possibility, all possible components, right? AX can have two components, B can, or A can have two components, B can have two components. This is a way of combining all possible permutations between them with that order n. And so let's begin by evaluating this. So let's see what this is equal to.
Do you normally do your transpose thing like that with your brackets like above and below, like the B?
Yeah, you're right. So this should be a transpose, right? Yeah, thank you. Is that what you meant?
Yeah.
Yes, that's correct. That's correct. So if I write this to be A and B, so then I didn't actually write it. I just said this is components, right? So if this is a row, then this is opposite, right? This is transpose. That's a table. But yeah, having said that, this is the outer product actually. That requires that transpose. Here it is without the transpose. These are just the components. It's in that sense, it's a slight small difference there between the outer product and this thing. So I haven't put that cross there, so I think I'm saying the same. But it's as far as inside goes, it is exactly the same idea. Okay. Is that any confusion there? Because I pointed out the transpose there, I hope this doesn't confuse. Okay. So be aware of it. But we won't be, so this is more for an insight. You will see how I'm going to use that regular. Okay. So these are two vectors. So think of it as a construction of two vectors. Or this is a matrix or a dyadic, right? Where is the dyadic is a matrix that has 9 components. That's the way you want to look at it. And most often we tend to use this in this course. We will use this kind of language. We will build dyadics. But let's see what this is equal to, right? Without going in any structure, let's explicitly do this, right? I know this in rectangular coordinates. I'm going to do this explicitly, obey my rules, right? So this is d by dx and d by dy plus k hat d by dz, right? That's what this is, right? So just check explicitly.
But you haven't included R.
Oh yeah, I'm going to write it. I was erasing stuff. Yeah, you could. Ahead of me. Yeah, thank you. So that's gradient. Yeah, good point. So this is x I plus y j plus z k, right? And the brackets is just to isolate the two quantities. There's no dot product here. Because if there was a dot here, there would be a dot product. There's no dot product. There's no cross product. In a sense, outer product or a direct product. Now, if you're multiplying two things, I had to distribute it all throughout. So notice what are the things coming in. Derivative of x with respect to x comes in. So there are quantities like this going up, e by dx. And the understanding here is that when I take a derivative, I have to operate on everything that's on the right. So here there is a quantity that's coming x and I hat. Okay. And it is, again, we have to use our principles of derivative and say that, oh, this is the, it distributes. So this is x and d by dx of I hat. This is I hat itself, that's clear, right? Partial derivative of x with respect to x is I hat. But this is 0, right? The unit vector does not change with position only in rectangular coordinates. If you were doing the same thing in cylindrical coordinates, this will contribute. So you want to keep that in mind. Very crucial. It's very easy to forget that unit vectors actually depend on position. And another situation, this could contribute. In this case, this is 0. Only in rectangular coordinates. So that's the advantage of rectangular coordinates often, that you have those zeros showing up. So that makes life a little easy. Otherwise, there are how many? Each one of them operates into 3 into 6, 6 into 3, 18 terms are there in this, right? But because I had K hat and K hat does not depend on position, many of that goes to 0. And so it's now easy to see. But I'm going to write this like this: I hat, right? This is the I hat. I have the two vectors because it's a dyadic, right? I hat, and that is d by. I'm going to. Yeah, so is that clear? No, let me write this d by dx of x plus I hat j hat d by dx of y. Right, which is 0, but I'm just explicitly writing it just for you to see the pattern. I hat k hat d by dx of z. And this is a sum. I can keep writing it in a single line, but just to show you the structure that this quantity has, I'm going to bring that rest of the three terms down. But this is sum. It doesn't matter where I write this. This is d by dy of x
Are you doing this just to show like the matrix form?
Yes, I'll write this again. Just I feel that it helps to write it, but maybe it is trivial. Okay? Sorry if it is too trivial. Okay. want it to sit in your head that there's a lot of zeros here, right? So this is 0, 0, 0, 0. And 3 of them are ones. Right? So this is equal to. Okay? So this is I hat plus j hat plus k hat. Okay. Notice what happened? The 3 unit vectors, and they all came and sat together. Right? I had, k hat, k hat, k hat, k hat. And if you think of it as a matrix, which it is not, this is a sum, right? These are 3 sums. But if you think of it as a matrix which has this component, this component, this component, that's an identity matrix also. So often we will write this as 1. Which has exactly the idea that this is an identity matrix. But we will see that it has much more meaning than this. We will promote it as a completeness statement, which probably we'll see that in another context. Okay. Any questions at this stage? Okay. So direct is that, right? Okay. So what if I do this? So this is rectangular, correct? What if I repeat this calculation in cylindrical? I'm not going to do that here.
You just get rho hat plus theta hat plus z hat, right?
That's very correct, actually, but that's not obvious, right? It's not very obvious why we should get that. Okay. So yeah, that's correct. And so this is a statement I'm making here. You'll see that in probably 1 week down the line when I'm doing curvilinear coordinates, probably this will be better. But here I'm just going to write that this is actually again rho hat plus phi hat plus z hat. In fact, it is still 1. It's a unitarity. So this gets a completely nice meaning now, right? The gradient operator acting on the position vector is not just one gradient and sitting in position. That's the completeness statement of the coordinate system itself. That's much bigger statement than saying that, oh, there is a gradient operator. It is some special operator, the position operator, something special. But this is a statement of the coordinate system itself. And that is how we want to use this. We don't want to work in coordinate systems. That's usually, at least insight-wise, not very useful. What we want to use
Excuse me, doctor.
Yes, please.
Does that apply also to the spherical coordinates?
Yes, spherical coordinates also. Yeah, maybe I should write that here. So this is cylindrical.
All right.
Get your favorite coordinate system. Let's say spheroidal coordinates. That's one of the slightly more complicated. Take any coordinate system, get the unit vectors. So let me write this here. So this is r hat plus phi hat. It's theta hat, right? Second one is doesn't matter. It's a sum. Theta hat plus phi hat. Phi hat is again equal to 1. And how do you get r hat? R hat from the surfaces, remember. So you can think of, imagine your favorite 3 surfaces, set of surfaces. Right? Remember, if you want to coordinatize your space, you need to have intersection of 3 surfaces. Right? What are the 3 surfaces in spherical coordinates?
Spheres, cones, and was it half planes?
Half planes, very good, right? So surface of equal radius, surface of equal theta, surface of equal phi, right? Surface of equal phi will be planes intersecting cylinders, right? So try to imagine that, and always, and you can come up with your own favorite coordinate system. It need not be the most convenient one, but once you have the surface, take the gradient operator, you get the unit vectors. Place the unit vectors like this. But your gradient operator acting on R. Yes.
Can I ask a question? If the position vector was not like x, y, and z, let's take it 2x squared, like 3y squared or something, is it be the same?
It will come out.
Will it be the same, or
it will be the same as far as those are three independent surfaces. Like you want to have three independent surfaces which intersect so that you can actually coordinatize the whole space. That's the harder part. Geometrically, you have to
and which
imagine.
will be the identity matrix?
There will always be the identity matrix. Yes, that's correct. If you can think of such, remember that not every function that you write will have that property that you can coordinatize the whole space. Is that clear what I said? So you cannot write arbitrarily anything and then get one. Yes, in that case it cannot, because not every function will satisfy the conditions that you can coordinatize the whole space. Right. But good ones are, for example, just to give you some examples of how you can coordinatize this out of this 11 coordinate systems I said, right? One of the non-trivial ones are when you use parabolas. So this is a parabola, right? So you can use this, and then intersection of this, like this. And probably, yeah, you can, I think, you can imagine, right? At least here you see the intersection, so probably you have to keep going like this. Again, extra credit, right? Try to draw the, so this is called parabolic coordinates. Whatever I cannot do, I will give it as extra credit. Right, so try to visualize parabolic coordinates in sense. Is that clear, the question? Visualize parabolic coordinates. That means to say you should get this out small boxes. Any coordinate you should be able to, it should be intersection of two surfaces. Spheroidal coordinates is something so that you have ellipses and then half planes. So those are various ones. And always in those coordinate systems, they will come out to be r hat, theta hat, phi hat, and that's equal to 1. Maybe there is this restriction that this might have to be orthogonal coordinates. Maybe that's one point I do see, because most of the times we work with orthogonal coordinates, and I have myself worked with only orthogonal coordinates. So maybe there is a restriction that this requires you to be in orthogonal coordinates. So, or it might be the other way. If it is not orthogonal, probably you cannot span the whole space. That's also possible. But those are my guesses.
This would be a way for you to check that, right? Like if you just picked three surfaces, and then you could take the gradient of the position vector, and if it's not complete, if you don't get the unit vector, then it doesn't span the whole space.
That's correct. Yeah. So that language for, I'm sure most or not everyone got that language. He used Moses used the language that if they are not complete, that means if it is not one, he used the language, then it is not complete. That's what I'm trying to convey here, and it will come out in the next 2 weeks. Hopefully, this will all fit in. So there is a completeness statement in there, and completeness, if you have seen from quantum mechanics, exactly the same completeness statement, but here in a much simpler form, the three-dimensional completeness statement. So you cannot write every vector in terms of these three unit vectors if it does not come out to be one. If it does not come out to be one, then every vector in that space cannot be written in terms of those three unit vectors. Good point. Yeah. So this is what we want to take home from all this. Right? That's it. So that will be one of our tools, if you want. Okay? And this is coordinate independent. whether it's spherical coordinate, I don't care which coordinate. It's a gradient operator acting on a position vector is always a unit a vector independent of the coordinates. And then we ask if that is the case. And by the way, since we have done index notations, right, this will be equal to gradient I and Rj, right? Two components. So this is actually this is not really equal, right? So this is so these are the components. These are the components of this vector. So in the same spirit as you often write, the vector A is equal to AI, but this is not really equal because these are the components of this vector. So in a sense, you have to say that this has all the information of this vector if you know the unit vectors. So that's so in that sense, this is if you're in, again, usually components are done in rectangular coordinates, then so we'll use this less often, but again we will use it. It will be very handy. So please be aware of that. But this is what we will use more as a mathematical structure. So then we have three more, right? So we have to do this. What is what's a scalar that you can construct out of it? What is that equal to? 3, right? So that's 3, right? And that's because this is I, right? So if you see this, or another way of seeing this is I hat, that's an identity, right? Plus J hat, plus K hat. That's without the dot product, but then put the dot product, there's a dot product in between these two, right? That's what comes in. And each one is 1, that's 3. Okay. And it's a scale, right? So that's very useful. See? And now that I've given you this, so how to see the operation for this del, then it should be relatively easy to see what is del cross. That's 0 because I'll put a cross now between each of this, and I cross I is 0. Right? So that's equal to 0. There's one more thing that is very useful, and that is as far as coordinate system goes, this is all that you need. But in our course, there's something that will come again and again, and that will be what is the gradient of the magnitude of R, right? So this is magnitude of R when there's no vector sign on top. So the magnitude of the position vector R. And what is that equal to? Can you?
R
That's
hat.
our, yeah, I will not say that's our hat, but I'm sure for others who see the first time, that's not very obvious at all what that is equal to. So let's evaluate this. Right? This is I hat, and now I'm going to do this in rectangular coordinates, but again, at the end, I will say that this is coordinate independent. Right? But I'm evaluating it in rectangular coordinate. But once we do this, then we don't want to do this again and again. That's the point, that we are getting some identities there. Then all through the course, we just use this as true statements, coordinate independent statements. That's the nice. This is being done in rectangular, but its result will be independent of each coordinate I work with. This is the magnitude of the position vector, which is x squared plus y squared of these. And notice this is again a statement, like half of you already stated the answer. This is gradient of R, that's a function, remember? So remember, your gradient operator is normal to the surface of constant r. So this will be in the r hat direction. Using that argument also, you can get that answer.
Can you adjust the board? I think the camera is migrated just a little bit.
Oh. Okay. I think I was doing it in a hurry. Let's see. Did it move around or was it not set?
I'm not sure. It's just kind of, we see the corner of the wall on the left. Move it just a little. There you go. That's perfect.
Okay. Okay, so I think I can erase this part. And this is, now let's just evaluate this. We did a very similar evaluation for cylindrical coordinates. So this comes out to be, if you actually do this, this is I hat x over x squared plus y squared plus z plus j hat y over x squared plus y squared plus z squared. Which is, if you think of it, the numerator is actually the position vector itself, right? The denominator is the magnitude of that, and that's r hat. So that's, we want to keep that in mind. Will again, very useful quantity. The gradient of the magnitude of r is actually r hat itself. Okay, so with this, let's try to do one of the extra credit problem that I gave last time. We should be equipped to do that. We thought of Gauss's theorem, and let's try to motivate that. And I have 20 minutes. So let's do yeah. So you have electric field, correct? Yeah, let's have the following quantity: gradient of dotted with vector r over r cube, right, which is the electric field. Right? Electric field due to a point charge is nothing but r hat over r cube. Right. So remember, your electric field due to a point charge at every place is 1 over 4 pi epsilon naught cube over that, and direction wise r over r cube. Of course, I put it on the origin. That's one point. If I move this, it is slightly different. If the charge is at the origin, that's fine. So that's a constant. So to avoid clutter, I just remove the whole thing. So that's this quantity. And the following operation is very typical of what we will see all through the course. Now, I have to be able to operate this, but I'm saying that I have all the ingredients out there. If I want to operate this, I have all the ingredients. I don't have to go into coordinate systems. This is very generic. So this is how I'll do it. The numerator and the denominator, I'll think of this as product of two quantities, and a gradient operator distributes on itself, right? So this is going to be gradient operator acting on the vector. So in that sense, it's a divergence. Right? And then 1 over r cube. And but now it has to act on the r cube also. So plus gradient operator. So now I'll be slightly careful since I'm crossing that. And in this case, it doesn't matter. So one should be careful about taking the dot is being replaced there, right? So I want to keep the order the same. How do I know that to write this on the left or to the right? Notice that you can think of this as having indices, right? If I were to put index I and j, this is I, that's j, that is I and j. The index being on the left or to the right, it matters. So you want to keep it on the left. So in this case, it doesn't matter because it's a symmetric quantity. So it will turn out that it is not very, you don't have to be very careful there. But in general, you want to be careful. Or if you're actually doing this very carefully, you might come across yourself, well, how do I know where to place it? Right? So be careful about that. Now, from this point on, so that was just simple distribution property of calculus. From this point on, we use our results. Right? That's 3. That's 3 over r cubed. And now, how do I do this? Right? Oh, that's I didn't see that, but we did do this, right? So in principle, you can use a chain rule. So I'll do gradients. So this is written as if this was 1 over r cubed. So this is minus 3 over r raised to 4 times gradient operator acting on r, right? I use chain rule to do this. So here, so for example, if I have f of g of x, right, and if I'm taking the derivative with respect to x, how do you do this? So this is d by dg, and then d over dx, right? So it's a chain rule, and this. So this is with the argument, right? The derivative with respect to the argument, and the derivative of the argument with respect to x, right? That's the chain rule. So that's what I did here. The gradient with respect to the argument, and then the derivative of the argument with respect to gradient of, oh sorry, I think I did the opposite, right? So this should have been, in this case also you have to be very careful, but again here we are fine. This I think is in the opposite order. Whenever there is that symmetry dependent quantity, it comes out very naturally. It's usually clear where it sits. Here again, as I said, it doesn't matter. Okay. And then we use our same result. This is r hat. Right. So notice I'm not using this is a coordinate independent way of doing this. This is 3 over r cubed minus this is r hat. This is 3 r hat dotted with vector r over r raised to 4, and notice that this is 3 over r cubed minus 3 over r cubed, which is of course 0, right? And all of you guys saw this in your extra credit exercise, right? So that is 0. If you were worried a little, one might argue that but often maybe it's not. This is probably when r is equal to 0, there seems to be an infinity, but then that's also infinity. You subtract, so there is a lot of discomfort there, like 2 large quantities, do you really subtract or not? And that's not very obvious what happens. So if you're concerned, maybe you will say that, okay, at r equal to 0, this is not true. Right? So this is r not equal to 0. But that's not very obvious. Like one can state that easily, it's looking at the answer, but right away, it's not very obvious whether the cancellation happens or not. In fact, sometimes it does happen. Sometimes it is okay to cancel that. But then the question comes, how do we decide when to cancel? That sometimes you do cancel infinities of that structure, and sometimes you don't cancel. So what's the strategy we are using? And that's where so suppose you did not realize this. Okay? You didn't realize. So that is really 0, but then that has to be consistent, right? So now, what are we meaning here? This is a quantity that we have everywhere in space. So let's say r hat over rq, or this is called left-hand side, right? So let's call this f of r. So this is f of r. Okay. So apparently, f of r is a function, scalar function, defined everywhere on space. And what we are saying is that that's zero. We're claiming that that's zero. In fact, again, with the caveat that r equal to 0, is this valid or not? And if there is a confusion over, or let's do a consistency check, right? So what we do is, what is the QR of f of r? Well, that's not complete, well-defined statement, because I haven't said volume integral on what, right? So let me do a volume integral on volume V, right? And that volume V, I say, is arbitrary, right? Any volume that you can think of, any closed, let's say any closed sphere anywhere in space. Pick your favorite sphere of favorite radius anywhere, and then you capture that and see how much that is. And you would say that, oh, that's zero everywhere. I can add as many zeros as I want on small elements. So this is at every point it is zero, except that that's again with that small issue that at r equal to 0, we have to be careful. But if you're not aware of that, you would say that this is 0 everywhere. So zeros added should give you 0. So that should be 0 in one sense. But then we want to ask that question carefully, right? So let's do this again, right? So let's do this carefully. So let's now, since it was any arbitrary volume, let me do this for a sphere. So let's say this V now is a sphere of radius r of r about origin, center at origin. So before I proceed, that's 10 minutes. Let me postpone the homework to next Friday, because I think there is this vector identities you have to do. I was hoping I will be able to cover that. I won't be able to. So is everyone here? Like 1, 2, 3. There are more numbers here. 5, 6. We have 8 of us? I thought we were 6 of us. So 6 plus 1, yeah, Khaled. 8, yes, that's correct. Because 6 plus Khaled is there, and Avinash is that's all. Yeah, yeah, thank you. Yeah, that's nice. 8 people. Yeah, yeah, okay. Yeah, sorry. I didn't correctly count before. Okay, sorry. Yeah, okay. I did add you guys on D-Dual, by the way. Khaled and good. Yeah, okay. Okay, sorry. So again, homework has been postponed. Okay, so hopefully, all of us are happy. Okay, so then I can go slow. I don't have to hurry on it. Yeah. So we are saying that it is when we evaluate it at a differential way, it seems to be 0 everywhere. Not sure about r equal to 0. You could have ignored that, or you might not if you don't pay attention closely. That you may not observe that. And then you say that, okay, if it is 0, then when you integrate over any volume, it should be 0. So let's pick a special volume. A special volume is a sphere, or one of the volume we are going to consider is a sphere of radius r centered at origin. That's easy to see. And f of r now is gradient of r over r cubed. But now I can use divergence theorem, right? What is divergence theorem? If you guys, so divergence theorem is about any volume. Repeat that.
Gauss's?
Yeah, Gauss's law is basically this uses divergence theorem. That's correct. Yeah. Gauss's law is using divergence theorem. Divergence theorem is a little could be any vector, right? So right.
Divergence is equal to the surface integral.
Is equal to the surface integral, right? So instead of this is not as evaluate this quantity everywhere in the inside of the volume. But instead, you say that, oh, I'm too lazy, I don't want to do that. That's 3 integrals. Instead, do 2 integrals, but now the price you pay is that now they are vectors. This is a scalar, integrate at every point, but now this is a vector dot product on the surface, only on the surface. So this is, again, this is the surface enclosing that volume. V need not be unique, right? But the surface that encloses that volume is unique, right? You can have more than one volumes that, and we have no, right? Because then there will be outside and inside. Yeah. So then I don't have to write this volume, right? Is that right? And curl that is there. So okay. Extra credit, right? Can you guys think of, because when it comes to curve, if I'm talking about a curve, yeah, so for example, if there is a curve, right? So this is a curve, and I ask, what is the surface it is enclosing? That's not unique, right? I can have a curve coming out and ending it. So for example,
No, it can't be a closed surface then, if that's what you're asking.
yeah, so
It has to be an open surface.
there has to be an open surface, you think?
Because
Okay.
if it's a closed surface, then the curl is equal to 0.
Yeah. So no, that's an independent thing. So I was thinking that might be a similar thing that happens here. So the question is,
So you have to use Gauss's theorem to change the volume to surface integral, right?
yeah. But again, so extra credit problem, right? So is the surface, is the volume enclosed by the surface unit? If that's the question. I don't know the answer to this question. Is the, seems like this has come before. Thought about this, but maybe.
I think you have the same question. That's what we think.
Yeah, and then I never answered it, I suppose, right? I thought about this, but I never answered. So is the, so yeah, I don't know the answer. Yeah, what's the question? Is the volume enclosed by a surface unique? So I guess I never.
What can you
I would have
what do you
to,
mean by unique exactly? It's one solution?
There should be only one volume you can think of. For example, what's the volume enclosed by the spherical shells, if you want. That's a sphere, solid sphere, right? And one could think that, oh, there is a boundary, but then that has a new boundary now, right? So you cannot think of it as a shell. So is that unique? Can you think of any surface? I'm now telling any surface, not just sphere. Is the volume unique inside?
Point.
well, but couldn't you come up with another surface that encloses the same volume?
The same volume will always have a unique surface, right? That I think will be unique.
Let's say we have a spherical shell
Uh-huh.
and with holes on top and bottom, and we put a cylinder, like a solid cylinder.
Uh-huh.
A surface has the surface that is enclosed. I mean, the volume enclosed by the surface. It's for both sphere and cylinder, right?
So you mean this?
Mm-hmm.
This way?
Yes.
Yeah. So volume is different, right? Because you removed the whole cylindrical volume there. Oh, now you're saying, oh, what is the volume?
It's the same surface that includes the volume, but the volume of the cylinder is different than the sphere itself.
Oh, right. See, there is this inside surface also, right? So inside also there is a surface. Are you accounting for that? Like this is also a surface inside. You see? So if I'm drawing this correct, I don't know how much I can. Or what I'm saying is that, okay, suppose two-dimensional, right? There is a surface here, right? And there is a surface inward also, correct? So that's a new surface that you've created. So if this is your volume, that's not the same as the whole sphere. So suddenly there is a surface at the shell. Right? So one has to be careful about that. But let's leave.
Well,
Yeah, go ahead.
I was just gonna say, like, you could draw a circle and you could draw a square and they could have the same volume, but they're two different surfaces. Or sorry, this in the two-dimensional case, the same area.
That's good, but then the surface is different, volume is different, completely different. But I was saying keep one of them fixed. Like keep one of them fixed, and then can you have two volumes having the same surface? I'm not saying surface area, you're thinking
Oh, I
about
see,
surface
two volumes
area.
having the same, okay, got it.
The
Yeah, yeah,
actual surface at every point, it should be the same.
Okay.
Kind of, right? So from outside you're looking and you have the same body, let's say, but inside you have difference or something like that. You want to make it dramatic. Okay. Yeah, I think, yeah, maybe I am confused. I'm not thinking correctly. But we don't need that. This discussion, I don't need that. Okay, that's just a digression. Thought for me. Okay. Divergence theorem tells that the volume integral of the divergence, this is the divergence, is equal to, forget the divergence, just get the electric field itself, take the dot product with the area element, right, and do it only on the surface. So I think I don't have to write that. Okay. So I don't have to say which. So this is just a closed integral. So closed surface integral. So I was not sure whether I should write that. So if I do that, then this is nothing but, this is now a closed integral. So this is dA dotted with R over R cubed. So I can write this as R hat over R squared. Right. This is the surface of a sphere, right, of constant radius. So this radius does not depend. Wherever you are on that surface, R is going to be the same. I can bring that outside that integral. So that's 1 over R squared times dA. And this area element on the sphere, what's the direction of this area element? Remember, area element is always perpendicular to the surface. That's in the R hat direction. And you're dotting it with R hat. Right. So that's a unit vector. So that's 1. So you see that that's 1 over R squared times, now the scalar area everywhere. So basically, it's the area of the sphere. Area of the sphere is 4 pi R squared. That R squared cancels. So notice the geometry coming into picture. This has nothing to do with electric field or anything. This is, if it was R squared, it cancels this. This is the area of the sphere, surface area of the sphere, that R squared is canceling. That's 4 pi. Right? So it cannot be 0 everywhere, right? Because apparently there exists a volume. I didn't even specify which radius. But every volume that encloses the origin, this is not 0, that's 4 pi. I can be as close to that as possible. So the answer seems to be not 0, but there are 2 of them. So if this is equal to 4 pi, not 0, it's a very clear number. That's 0 and 4 pi. If volume, or here, if volume includes origin and otherwise. Okay, so this is surely not, so there's something special that happens when R is equal to 0. Right? And it is 0 everywhere, so it probably has to be infinite. So it must be infinite at that point. So these two really do not cancel out. It actually is it is infinity, and we will see that more clearly later on. So if we are going to define a delta function there. So if you have already seen what a delta function is, this will come out to be a delta function. But we have to motivate that. So what is delta function? So that cancellation that I talked about, that's where the delta function property will come from. Delta function is something that has this power just right of the right kind that there are cancellations involved. And we will, remember this argument. This is the central idea of electrodynamics in a sense. This infinity and 0 showing up and it capturing the point. So if you want, this is a source. Like this is a source of the electric field. So that point charge, so this is basically the point charge, right? If I divided it out by 4 pi, the point charge which is actually generating the electric field. So electric field is generated by a source which is of this kind, a very special quantity there. So try to think along that line, and we will. The whole course is probably going to give you more feel of the whole thing. But let me stop here. 5 minutes crossed. Thank you for listening.
Thank you.
Yeah. Let's see.
Bye.
Bye, Michael.
See you later.
Yeah, see you. Enjoy.